Good morning, everybody. This is an earlier morning for me than for you because I'm about like 3 hours behind right now and I'm not a morning person. So I'm going to give you my but actually I talk better when it's not ideal, so this should be optimal. So I wanted to start about a little story about big data is a word that we get, it gets thrown around a lot, and so is surface water, and so what? What does this actually mean? And so I put this picture here as a reminder to what this actually really means. And so this is a picture on the banks of the Yukon River in Circle. And we're looking at a boat, that belongs to a guy named Albert Carroll. And he had just gotten back from pulling his net, and we're looking at some fall chum. This was back in early September of last year. And man, were those chum really good. They were delicious. He was really nice, and he gave us a couple. And they were really phenomenal. And so to me, this represents where the rubber starts to really hit the road of when we think about surface water change. And so Albert's been living up in Circle his whole life. This is how he gets his food, at least for this part of the year. Like the salmon is a really important part of his diet. This is how he feeds his dogs. This boat actually had a really interesting story. He looked at this boat on the side of the Yukon River for about 15 years where it was rotting. And then he finally managed to track down the owner and buy it. And this is where the road ends as well, actually. So to go any further on this landscape, you're looking at the primary source of transportation, which is a boat. And so in the Arctic, that's a really easy thing to forget, is that our roads are really expensive to build, and how do we get around otherwise? And well, some of us own planes. Most of us can own a boat, or at least know somebody that owns a boat. And when the boat season ends, then those rivers are still our primary transportation network, because ideally they freeze and you can snow machine on them, or drive a dog sled, or ski if you want, do whatever you want. So I think it's important when we're talking about, like I said, these big concept topics to really think about these really important human stories. And Albert's not in the picture because I don't think he wanted to be in the picture, but his boat is, like I said, he was very proud of this boat. So this is a picture of surface water in the Russian Arctic, and surface water in the Arctic and lakes in particular, are more abundant in this region than anywhere else in the world. And there's a lot of reasons for that, and we can talk about that in depth if you want later. But what you should really take home from this is that understanding where water is and how it's changing is really important for those local processes that we talked about. The regional effects, because people tend to stay in a specific region, but they also have major implications for global processes, including the carbon and methane cycle, and a number of other important ocean processes and all sorts of stuff. And the Arctic is also just simply a pretty big area in the world. So I put this slide, and I can go back for a second. So this is essentially the normal one that you see on a satellite image. Perfect. This is a classified image. So our ability to be able to pull out water really quickly has gotten much better. And there's been a lot of time and effort on the global scale made to be able to do this, because water is so important globally, but it's equally important, like we just talked about, in these Arctic areas. And so when I never thought I would get into big data, but then I did, because where the water is so important. And not only from a spatial dimension, and often when we think about big data, we think about going into finer detail, spatial detail about things. But in this case, this is really giving us the capacity to look at long time series, because water, especially in these environments, is really variable, and it's really, really tricky. And so although you care about where it is over, in that place, you really care about where it is in that place over time. And making some of those trade-offs is interesting. And the big thing when we've been looking at surface water studies is that you really want to look at very, very broad areas because there's so much of it, right? And so when we look at simply like a single watershed, that's great. But what I can tell you from like a lot of the remote sensing side is that for the amount of effort that you put into doing like a couple watersheds, like a couple of the major watersheds, you can pretty much do the entire Pan-Arctic now if you have a good plan. And so this is changing how we think about and do science, and it's changing in some really important ways. My talk, I'm going to go and we're going to talk for a little bit about like what I found, but we're really not going to spend too much time on that because we could talk for a long time about that, and I have a whole paper on it. But what we're going to talk about today is the next paper that I'm actually just about to submit, and it's more how and why I did what I did, which I think for this audience is probably like A, more interesting, and B, very useful because the questions and how I ask them are very applicable to a wide variety of fields, and what I did, you totally will probably actually want to do for your own reasons, just on a different topic area. So we're going to go through some of the theoretical, computational, and communication improvements that I made on my project. And so the whole point of this is that essentially at this point, like this idea of integrating big data is the norm in doing this sort of work. And because it's not, like there's still some challenges to doing the work, but those challenges are absolutely worth the outputs and the improvements that you're getting in the understanding. And so in my opinion, we've now crossed the threshold of like the computational side really holding us back, and now it's more a pressing need for adoption, and especially when we look at like both the policy implications and the application side, we really, really need this transition to be happening really quickly, actually. So the motivation for this work was originally, I was working with the NSF search program, and so it's great that ARCIS was organizing this because they're heavily involved in the search program. And it started off as kind of a policy synthesis project about where surface water was in the Arctic and where it was changing. In order to do this work, I have utilized Google Earth Engine quite extensively. And so, so all of the work that we're going to see is mostly done on Earth Engine. And I'm not going to go into too much detail about it, but I will at the end highlight like just some of the super easy things that Earth Engine can do. But my overall approach is repeatable on any system. It's not unique to Earth Engine. It's just that Earth Engine makes it really easy for a number of reasons to do this sort of work. So what did I find? Well, when you look at where water is, everywhere that there's permafrost in the northern hemisphere, it covers an area of 1,203,655 kilometers squared from 1984 to 2018. And so of that, 89% remains water. We're losing about 3% of that water overall. So that means that it started as water sometime early in that period, and by the end of the time, it had disappeared. And we're gaining actually 8% of the total area. And so that meant that it started as land and it transitioned to water. And so when we're doing these big sorts of projects, the thing that I can tell you is that when you have as much data as we do on this, so these numbers are coming from surface water information that was derived out of the Landsat archive, and it's all based on the global surface water data set, and we're going to go through that. I did more things with that in a second. But the big thing is that the main data set was repeated globally. It's actually originally a global product, and so that allows us to take these results and find that of all of the areas in the northern hemisphere that have permafrost and all of that water, the stable water areas comprise 30% of global permanent and seasonal water, while gains and losses each make up 12% respectively of the global totals. So it allows you to get perspective on your work in ways that when you do small areas are just not possible. But you can now take your small areas and compare it to these big numbers and be able to get that like broader perspective. And so what did I do to get here? Well, I did a lot of things, many things. And essentially I made myself a big problem. And that's why this is a big data problem. And so I started at the top. So that the gist of it is that I use like 7 completely different data sets in order to get to the numbers that we were just talking about. And so it starts with taking that global surface water data set, which contains actually a number of different data sets. And I started off by looking at their like final summaries. And they were a little bit more complicated. And so I was like, well, what do I actually want to know? And I was like, well, pretty much I just want to know if it stays water, if it's gaining, or if it's losing. And so I took their big summary project, or data set, sorry, and I reclassified into that, or classified it into those classes. And we looked at it, and I could tell that it just wasn't like quite right in some of the areas that I like knew. And I was like, well, what do I do about that? And I was like, well, there's other techniques out there that exist and other papers that have been published, so why don't I try applying one of the other models to some of the monthly data sets and recalculate a second option. And so that's what I did, is I took a technique, it's a regression technique from, it's a product called the Aqua Monitor, and it's also a big global product. It uses the Landsat archive. And I took their approach and I applied it to this data set. And so now I have 2 water models, and they're different. So what do? Do you throw out one of them? No, you shouldn't throw out one of them. You should ask yourself, like, is there legitimate reasons why they can be different? Because they're now playing off the same data set. And they're both valid, just in like slightly different ways. So then I was like, well, now I'll just calculate a third version of it. And I'll use a very standard technique. So I used a Mann-Kendall Sense-Thiel approach to calculate a third version of it, which ended up, as we'll take a look in a second, to be very conservative, actually. And so now I have 3. I'm like, okay, well, the climatologists that I work with have a pretty good technique to deal with disparate models. It's called they average them. I was like, that's what I'll do. I'll average them. This will be a great idea. So I started to be like, well, how am I going to average them? So if we start at the bottom here, we have a fair amount of permafrost information that's available. And so there was existing information on the Pan-Arctic, not everywhere that I was looking at, but most places, on thermokarst probability and also the landform type. And some new data had just come out that used MODIS temperature data, actually, to calculate new estimates of permafrost extent and permafrost temperature. And so that's from the Globe Permafrost product. And I was like, okay, so I know lots about permafrost, and now I have even more like categories to deal with. What do I do? And so what I did is I compressed all the permafrost data together. So I would get areas that I knew had consistent permafrost characteristics. And then I took the water and I would average them over those areas. But I wanted to know one more thing. And this is where it gets a little bit complicated, and we're gonna like move pretty quickly. I wanted to know if it was in rivers, lakes, and then if it wasn't in a river or lake, it would be in a pond. And so ponds are just, I call it the catch-all term, and it can be a lot of things, but pond is really easy to talk about, and so that's what we call it now. And getting to the rivers and the lakes, but the rivers in particular, was a big pain in my butt. And so that's what we're gonna talk about in just a second. So these are some of the overall findings, and the big things for you to know is where there's more water doesn't necessarily correlate to where there's more change, and that's because of superficial geology. But it's a pretty straightforward message to take home. And so in this paper, I also go into tons of detail about looking at the relationship between water and the different permafrost types. And the big take home when you look at it everywhere is that you would think that warmer temperatures or higher ice would be associated with more change, and that's not actually what we see. What we do see is that lake loss and river loss are the things that are most associated using a generalized linear model to permafrost change. Ponds don't associate very well at all, and the gains associate permafrost characteristics are responsible for about 50% of the change, essentially, whereas those losses, it's 78 and like 90%. So what did I do, and what do you actually care about? So I did these 5 things, which we're gonna like go through quickly, but I want you to be thinking about them. And the first is getting to the lakes and the rivers. So the best thing that I can tell you is that lakes have been done and have been done for a long time in the Arctic, but nobody ever did the rivers. And doing the rivers simply meant that you had to go and extrapolate where the rivers were. And we did that by using a distance calculation, actually, based on the maximum water extent around rivers. And so it's actually a really simple solution to solving a fairly complicated problem. But there, as we just went through, some very good reasons why you would take the time to do that. This is just quickly showing those differences in models. And you'll see on this left-hand side that the differences between the overall water and the different classes aren't that big. But when you start to look at the changes on this side, there are some very big differences in the models, super big differences. So that idea of why you would combine multiple ones and go through all this effort is a very interesting theoretical discussion to have, but big data allows you to drive fairly deeply into this. This is, if I can tell you anything, probably the most useful thing for you to take home from this talk, actually, other than the next thing I'm going to show you. And it's this idea of how you take that like over 9,000 combinations and efficiently compute summaries out of it. The trick is that you add things together. And so I took all of my water data, the change data, and then whether or not it was in my river, lake, or pond, and I would add those together, so I would only get 9 classes, and then I could run a loop for each one of those 3 water models fairly efficiently. And then when I had all of my permafrost data, I could go and use those vectors to then essentially map back and forth between the 2 of them. And the really sneaky trick that took my whole analysis from taking 2 to 3 weeks down to 3 days was that you can, within that vector data, which actually is originally at a kilometer spatial resolution, you can go and calculate the area, because that's what I want at the end of it, right? I just want the area of things in that place. And you calculate it for that area, and then you write that area value to a 1 kilometer raster instead. And so when you do the big vector summary of the entire area, you're summarizing not off the original 30-meter pixels, but you're summarizing off the area of 1 kilometer pixels that have already been derived from the 30-meter data. And it goes way faster. And so when we talk about transmitting data and how much data that we're transmitting, those 2 things are a super sneaky computational trick that will save you a lot of time, a ton of time. And they're actually a pretty big deal. And so then when you've saved yourself all that time, you might as well do the last thing, which is that when you work in these environments now, you can build web apps fairly easily to display your data. And so everybody always asks me when I do this work, well, what does it look like here? And honestly, I don't know, because I look at everything. And so I built a very nice web app, actually, that's live already, that allows you to look at all of the things that I just talked about, so gain, loss, gross, total water, in all of those different classes. And it's got the associated permafrost layers, and you can zoom in and you can look at it. And so then you can also see that, what a 1 kilometer pixel looks like. So you can see, like I said, the effect of that little trick that I'm playing from going to the 30-meter data. And building a web app, once you've built a couple of them, is really, really quick, actually. And so that's a big advantage of Google Earth Engine, is that all that surface water data was there. I uploaded a whole bunch of the lake and the permafrost data and the river data. But once it was all there, it makes it really easy to build a web app quite quickly, actually, which allows people to go and look at your data and tell you how good it looks. And so the policy implications for these sorts of things are fairly extensive, but essentially we're talking about changes in permafrost, so thermokarst and thermal erosion, and obviously this has an effect on communities. So the nice thing about my approach is that it standardizes how we look at water in the Pan-Arctic. So if you have a community in Canada and they're like, I'm seeing these changes, and a community in Alaska says, I'm seeing these changes, you can actually compare it in a fairly robust way. Are the changes like similar in magnitude? What does it look like for their like water forms? All sorts of things. So I call this project the tip of the iceberg. But the big take home is that this sort of approach is the new norm, absolutely. And it gives us the capacity to really dive much deeper. And I view this as like pretty much being a summary of where we're going with things. Perfect. And so now that I have 0 minutes, what could you do with this? Well, this is other data that's on Earth Engine already. And so we're looking at the Sentinel-5 methane data, and we're also looking at the ERA5 precip data, and I've like aggregated it to the monthly scale already. And so there's really obvious opportunities to link to other data sets, to look at relationships. And why didn't I do that? Because I wanted you to pay attention to what I was doing in the first place, because it actually represents a fairly major improvement. And it's an important one to be able to look at those relationships to other data sets. And so that amount of summarizing that I'm doing is actually really critical to being able to efficiently link and understand how to prioritize where to go. And getting back to my little story about Circle on the Yukon River, so for all that I was looking at the boat, if you turned just a little bit more, this is where they're hardening the riverbank because they're having serious erosion in the community. And this community also has serious permafrost issues. And so a lot of what we're talking about is very linked, but it has a huge human component. And so how do you look at areas that are very sensitive and have a lot of legitimate issues and get an overall broad view of how to compare them? And so that's what my work tries to address. So.